For the final example problem on the topic of work, we have a ball rolling across a table. That ball rolls off the table, hits the ground, and we are asked, what is the work done by gravity on the ball, and how fast is the ball moving when it hits the ground? So a theme of this particular example problem is going to be that when you are going through a problem on the topic of work, you don't necessarily need to be given every piece of information to solve a question. So, for example, if I wanted to, we could have answered the second part of this problem back in chapter 3. We talked about projectile motion. If we are asked what is the final speed of the ball, we could say, well, speed is related to velocity because speed is the magnitude of the velocity vector. So I could say the speed of the ball will be square root vx squared final plus vy squared final. Vx will be 2 because the acceleration in the x direction is 0. Vy we can solve for because the acceleration due to gravity will be negative 9.8. We find the components of the velocity vector when the ball is about to hit the ground. We find the speed. But there is another way we could solve that question. So the first part of this problem involves what is the work done on the ball by the force of gravity. So we said that work is related to the force acting on an object by work is Fd cos theta. Now, in this example problem, the work done is the work by gravity, so the force we consider will be the force of gravity. The force of gravity always pulls downward on the ball. So the force of gravity is going to be pulling on the ball straight down. I could draw the force of gravity to look something like this. Here is that force of gravity vector. Now, the displacement of the ball is going to be a vector that in this diagram points down and to the right. Here's the initial position of the ball. Here is the final position of the ball. So the displacement vector is going to look something like this. Now, the first thing we might think is we look at this equation. Okay, what is the force of gravity? Well, the strength of the gravitational force is the mass of the ball times 9.8. So we're given that the mass of the ball is 0.1. So I could say force of gravity is equal to 0.1, 9.8. So I get 0.98 for the strength of the gravitational force. Well, what about these other two terms? Theta is the angle between this vector d and the force of gravity vector. So theta is going to be this angle right here. And d is going to be the magnitude of the displacement. So d is whatever this distance is. We don't have either of those pieces of information. However, let's look at this diagram a bit more closely. I could look at this diagram and say, even though I don't know d, the total displacement of the ball, even though I don't know the angle, I still see a right triangle in this image. There is a right triangle right over here. Here is the distance that the ball lands away from the table. Here is the height of the table. And this vector d forms the hypotenuse of that right triangle. And the more closely I look at it, I could say the height of the table is equal to d cos theta. So I could say the height of the table, which is 0.8 meters, is equal to d cosine theta. Let's look at what we have. I don't know d, I don't know cosine theta, but I know what the product of these two terms is. It's 0.8, which is the height of the table. So this entire term right here is going to be equal to 0.8. So now, even though I don't know how far away from the table the ball lands, I still have enough information to find the work done by gravity. So I could say the work done by gravity on the ball is going to be the force of gravity on the ball, 0.98, times d times cosine theta. Again, I don't know what those two terms individually are, but I do know that their product is going to be 0.8. So I set that to be 0.8. So I could plug and multiply these numbers together, and I find the work of gravity that gravity does on the ball is 0.789 joules. Now, hypothetically, I could have found the magnitude of this vector d and this angle if we had gone back to chapter 3 material, 2D motion. I could have said if I know how fast the ball is moving, I could find the time it takes the ball to fall through the air. When I know how long it takes the ball to hit the ground, I could then use one of the equations of 2D motion to find how far away the ball lands from the table. If I know this horizontal distance and I know this vertical distance, I could then use the Pythagorean theorem and trigonometry to find the magnitude of the displacement and this angle. But that would have been a lot more steps. Solving a problem like this in the context of work made our life a lot simpler and made things go a lot quicker. In the next part of this problem, we are asked how fast is the ball traveling when it is about to hit the ground. Basically, what is the speed when it hits the ground? What is this V final? To determine V final, I am going to use the work kinetic energy theorem. So the work kinetic energy theorem is very useful in this entire chapter whenever you encounter a work problem. It says the total work done on an object, W net, is equal to the change in the object's kinetic energy. Well, when the ball is in the air, is there any other force acting on the ball? No, there is not. We are neglecting air resistance. We're not going to count that. The only force that is affecting the ball is gravity. So the total work done will be the work done by gravity. We found the work done by gravity. That's 0.789. So I could write that as 0.789. Now, what is the ball's change in kinetic energy? Well, that's kinetic energy final minus kinetic energy initial. So I could write this as 1/2 times the mass of the ball, V final square, minus 1/2 times the mass of the ball, times V initial square. We know what V initial is. V initial is 2 meters per second. We are given the mass of the ball. So I could write this as 0.789 is equal to 1/2 times 0.1 V final square minus 1/2 0.1 times 2 square. And if I plug these numbers through a calculator, solve for V final, I find that the final speed of the ball is going to be V final equals 4.4 meter per second. So again, I would like to emphasize with this problem, notice that I did not need to erase the board once in this. Determining the work done by gravity was very quick when I was able to recognize that I don't know d, I don't know cosine theta, but it's okay if I don't know those terms individually because I recognize the height of the table as the product of d and cosine theta. Also, I don't need to know how far away the ball landed from the table. I know gravity is the only thing affecting the ball's motion. I know gravity is going to be causing the ball to speed up, move faster and faster. And so gravity is going to give this much kinetic energy to the ball. If the ball initially had this much kinetic energy, gravity will give this much more. And then I could relate kinetic energy to speed to determine the final speed of the ball.